We're going to look at another interacting objects problem. Hopefully you've already seen the video on the Atwood machine, because this is going to be a variation of that, and it's actually potentially a little bit easier to understand. It's just, not as historically relevant. So we are going to have a block that is on a frictionless surface in this version of the problem. And there's a rope from that block leading to a hanging weight. And despite the size of these things that I just drew, we're going to call that one little m, and we're going to call that one big M, pretty analogous to what we did last time. So we are going to set up, again, a sort of typical coordinate system here, so that the mass little m only moves in the x direction, and the mass big M only moves in the y direction. So let's set up our free body diagrams. So get in there. Okay, so for little m, we've got the weight of little m, we've got a normal force on little m, and then we've got tension. I'm going to make that 4. Yeah, 4 is probably fine. And I'm going to call this T1. We don't actually need to put a subscript for the tension for the normal force, because there's not going to be another normal force, because this thing is just hanging. Now, the thing that we need to know is, just like we saw before with ideal ropes and pulleys, the tension at any point in this rope is going to be the same. So if the green block pulls down with 10 newtons here, that 10 newtons is going to make it to the cart over here. So T1 and this tension, T2, which is going up along the rope from mass big M, have the same number of dots and of blocks, of spaces. They're the same. We do know that the acceleration for big M is going to be downward, because there's really nothing holding it up. So this is going to be big mg. I'm not going to write out the tau chart this time. It is very similar to what we had before. But one thing I am going to point out is, with our constraints on the acceleration and our pairs of forces, the acceleration of the block x is going to, the block little m is in the x direction, and the acceleration of the block m is in the y direction, and specifically it's pointing downward. So I'm going to call this, what am I going to call this? Call it a little m x. Okay. We could write these as vectors, right? We could write a little m is equal to magnitude of I a hat, and a big M is equal to negative a j hat. In either case, we want to find the acceleration magnitude, just like in the previous problem. I didn't say that out loud until now, though. For our force pairs, the magnitude of the tensions are the same, and so we're just going to call those big T. Okay, so we write out our Newton's laws. We've got the sum of forces in the x direction is equal to little m ax. We could potentially also have y direction for little m. It's going to turn out that we don't need it in this example, but in the next one we will. So I'm going to erase it for now. and we'll get it a little bit later, but we do need the y forces on big M. So what are the x forces on little m? It's just t1. That's it. And what is the acceleration in the x direction? It's a. And we already said that we'll call t1, the magnitude of that is equal to t. In the y direction, we have t2 pointing up, we have weight pointing down, and that is equal to the mass times the acceleration in the y direction, which is negative a. And just like before, the magnitude of t2 is just what we're calling t. Well, this might look familiar. We've got two equations, two unknowns. So you know what I like to do here if you watch the other video, which you should have, otherwise what are you doing here? And we've got t minus mg is equal to, I'm going to write this as negative ma. And just like before, I'm going to subtract this equation by switching the sign of each term and then adding these two rows together. So we've got a t minus a t plus an mg plus a little ma plus a big Ma. You can see that the tensions cancel out, that's why I did it. And we have big mg over little m plus big M is equal to acceleration. Okay. In the next video, I'm going to show you a shortcut that might be a little brain breaking, but can be helpful in these kinds of problems.